No, it's not, the distance never really bothered me as
All right, so
personal reasons.
this is your time. I'm here to help you. I like having these sessions because Professor Aline Chubb, she was the thermodynamics professor that I had in undergraduate, she would have review sessions. She was the first professor I ever had that would have a review session. I was like, I really appreciated that, and I thought, you know, I would like to give a review session because it was done for me. I think it's a good thing to try to do it for other people. Get credit for showing up. It's good.
I don't think I signed that.
I just gave it to him just now, so hopefully it'll come
It
around
looked
to
like
you.
you were taking it.
And no, I had 2 sheets here, and I'm like, you don't quite need 2 sheets yet. Of course, you just use the back if you want to. So I have practice problems that are available, and I think I've already posted solutions, at least for my classes. I don't know, did Dr. Orlip give you, did he give you practice problems for the exam, final exam? He usually shares the same stuff I give out.
He
So.
probably did, but I just haven't checked.
Yeah, you should check. But I want to leave those for you. Those are ones from Coast Guard Academy, or at least some of them are. Can't remember. Actually, I have them in front of me. So here's actually some of those practice problems. So a little preliminary stuff. I don't know how great this is going to show up on the camera here. So the material covered since exam 3, we had mass moment of inertia, rigid body motion, Newton's second law, rigid body motion, work and energy, and then we just recently had rigid body motion, impulse momentum / impacts or eccentric impacts. So those are the types of problems you can expect to be on exam 3. I'm not, people ask all the time, is it cumulative? Well, by the nature of the course, it's cumulative. I will ask specifically a rigid body acceleration problem, so which will involve probably rigid body velocity. You kind of need to do that to get the angular velocity, and I won't specify which method you'll have to use, but I would think, is that true? I would say you refresh yourself on ICR and go 3-diagram method is what I think I would ask if I were to ask something specifically. So here's the locations of the new material or most recent material on the equation sheets. It's not so much different. You don't really even need this equation sheet, personally. I think you should probably get used to it, maybe not have memorized it. So it's just there as sort of like a security blanket. Wouldn't spend too much time staring at it during an exam, hoping something comes up. But what it also does is when you have a question during an exam and you come up to me, sometimes I will maybe point to a place on the equation sheet and maybe ask you a question, and hopefully that will jog your memory and nudge you back into the right zone, into the right lane. We want to try, this is impulse control on my part to have to tell you this, but you want to try to deviate from the mindset of equation hunting. Like looking for, I didn't know what equation to use kind of thing. Like, well, don't think of it that way, right? Think of what concepts. All those equations represent concepts and ideas that you're trying to apply. I know it sounds like nuance, but it's a difference. There's a difference to it. So here was from spring of 2016 to Coast Guard Academy. That's a Newton's second law problem. Spring 2017, my last year. Yeah, that was my last year at the Coast Guard Academy. I didn't write this problem, I can tell, because I would have made a prettier picture. Oh, I'm sorry, I would have put my coldest feelings. Spring 14, that was a long time ago. Spring 14, okay, so this is a Newton's second law, impulse and momentum. That's kind of, you can tell right there, this is the last topic we just covered, right? Because you have collision that's happening on sort of a, and that does look like it might have been me, yeah. But not my handwriting, that's Alicia Garcia. This was mine because it was a silly looking thing. There's a work energy problem. I tried to make something complicated. Something I would change, I would no longer do this, but I used to, I asked all of these things to make it easier to grade, because I get boom, boom, I'd assign like a thing to a point value to each of those steps. But I don't want you to just me to hold your hand and walk through it. So just keep that in mind when we're looking at this. My good friend Sean Munnis wrote this problem. It's like an elevator. It's actually right out of the, no, not, it was out of a different book. Impulse and momentum. That looks like kind of like me, but it's Alicia's handwriting. Work energy. Here's this is definitely me. This is a ballistic pendulum. So this is really close to what we just covered. This is definitely me. So this is really various topics. So there are chances, not too much, but there's only so many problems I can ask during. So this was trying to get some more of that dependent motion stuff. This is with particles for polar coordinates. Here's a particle for work energy, because you can see the spring, the boing thing. Here's an acceleration problem. Here's a ballistic pendulum kind of problem, so sort of like that. A work energy. Oh, both Newton's second law and work energy. This is definitely a impulse momentum collision problem. This is mass moment of inertia, another mass moment of inertia. I generally don't emphasize that all that much, so probably you wouldn't need to spend a lot of time doing that. There's a bunch of them right there in a row. I have some, okay, so those are the stuff that's already posted. Here's some that from my book that, some of these are kind of basic. Like this is a pretty good problem just because it is simple. This is Newton's second law. Another Newton's second law here. This is a very, this is a good problem because it is a simple, but then it does reveal, if you can do it, that you're capable of solving it does measure. If you can't do it, it measures that you can't do it. Yeah, this is not a simple problem, so I probably wouldn't ask it. It involves a bunch of more steps in time. Don't know if I go there. This is also like a really long problem. But here's okay, this is actually almost identical to an earlier one that we just showed. And this is this is a deceptive problem. What do you think you'd use on this? Like look at the wording. Well, first when you look at the problem, what do you think it's going to be? You think so, right? Because you see the spring. That was the trap. It's the trap. You think you want to go work energy. Why can't you do work energy?
Because B isn't massless?
Not quite. It's because it's not going between two different points. You want to do it in instantaneous. So you can't quite do it, you can't do an instantaneous thing with work energy. It's got to be a Newton's second law. Even when it's impulse and momentum, you really need to have some time have elapsed. Although that's not 100% true. I'm sorry, I'll take that back because it could be a really small amount of time, as with impact. Right? Impact has a very, very small amount of time, but we do have there is a bit of two separate points in time happening, although they could be very, very small, but before impact and then after impact, even though we're talking like microseconds in between. So that's that was one I put in there. And then I also have included a link and some that I just happen to pick off from Must. Anybody tried any of these before? This is the Missouri University of Science and Technology, Must. Anyway, it's a nice this website. It's been up there for a long time. I guess he hasn't been updating it for a long time there. But he's got a ton of stuff. If you go to, I know I'm not sure Dr. Orlip has the same links as I do on his Blackboard. But we'll get to an example soon. So please start thinking of problem types or specific problems that you would like to go through. I'm riffing right now, but I'll finish this and then get to the soliciting examples and problems. Useful links and resources, and I think it'll be down at the bottom. Old problems from Missouri University of Science and Technology. So if you go to that website, you can see there's a ton of problems. Every one of these things is an individual problem. And then he has I think there is some overlap between these right here. This is Jeff Thomas, must be a guy that's there. Since fall of '99, so this has been a while since this was up here. But then I think these other stuff up here is from Dr. Ralph Floria. So there's two different professors. What's nice about these is they're exam type problems, right? They're just long enough to have been done there. I do think the solutions that they give in here are a little deceptive in how easy they are to do, because they do them in very few steps, and I think you would want to break them up a little bit if you're a student to think through the things. It makes things look like a little easier than they are sometimes. But anyway, that's some background and some suggestions, and I will open up the floor to your questions there. What else is that one? There's some must ones in there. So anybody? No wrong questions.
But there's a question that will be 90%.
Okay, I know you're gonna. I see how I even was kind of predicting this. When is Alejandro gonna ask me to put the exam up there for him? I think we've done this every single. This is the fourth time in a row, right?
Oh yeah.
Hey, consistency. That is a admirable trait. Sometimes.
I am very disciplined, so.
That's great. Is that what you consider discipline? Consider discipline what they tried to instill in me at the Merchant Marine Academy. Didn't take.
Can we do one oriented around like Newton's second law?
Okay.
Setting?
Let's see if this one is. Nope. 5 feet up the slope. Let's do this one. It's got a lot of stuff. This might be too long for an exam problem, but I don't know. I should know the answer to this one, but I don't think I do. So I guess I can't get it wrong. So, block A is 20 kilograms. It's going up with the slope is 20 degrees. Let me write this thing out. Boing. Oh, I think blue has to go away. I hope I can do it. All right, and then it's a 3D print this thing, right? Make it bigger. Now that I have my 3D printer working again, I'm going to start making every single problem. I said I was going to do that, but I never got it working until just the other day.
What was wrong with it?
I don't want to admit what was wrong with it.
Was it a SLS or FDM printer?
It was an Ender 5. I don't know if we ever, I don't know what those acronyms stand for.
FDM is where they just build it by layer. SLS is when they use the ultra sensitive, what's it called?
The ultraviolet light? No, okay, I don't know. It's a PLA, it's just a PLA.
Okay.
Well, it's supposed to be PLA, so that's the, I bought off of Amazon what seemed like a really good deal.
Prime?
I had PETG instead of PLA. And I had a bunch of it, so every time I was like, ooh, I think it's a bad batch, so I tried the other one. We're talking 2 years. 2 years are worth of struggling with this thing. So again, I don't. By the way, I don't want to no take backs. I want to take that back, and that's recorded too. Right, great. Okay. 20 degrees, and this is 20 kilograms. Is that right? What is B? Okay, no, this is 40 kilograms. And by inacceptable cable, this is 60. This guy's large. And what's the diameter? Okay, this is K is equal to 2,000 newtons per meter. I'm gonna make sure that.
The radius of B is 22 meters.
Where is it? Oh yeah, there you go. coefficient of friction is 0.2. And we want to find the tension. And we have to be specific though. Find the tension of the cable between A and B. So right in here. So FT AB. There you go. FTAB. Was it,
And then it says, del is 0.02 meters.
oh yeah. Sorry, thank you. So del is 0.02 meters. All right, so we could for that use the display. All right, how to start this? What do you think to do to start?
Find the force of friction on block block A.
FBDs and IBDs.
Mm-hmm. Two great answers. FBD, IBD. I'm partial to green for weight, green for gravity. And we're in SI units, so mg is down that direction. X prime and Y prime. So we have our angle right there of theta. So we're gonna have a normal force, Fn. And which way is friction going? Down and to the left, up and to the right.
Well,
Down
which
to the
way is the
left.
blocks go? Which way is the block going?
So it's true, okay. You're both right. And we're predicting that chances are it's going, this is dropping downwards, right? But you don't know. We don't know actually, because this spring could be stretching so much that it's actually pulling this thing up. That would be a dirtbag thing to do. But it's possible. You know what would happen is all the signs are going to get messed up. So we can assume one direction and be on the lookout that we got it wrong. By the way, the same thing would happen where work energy, but what you might find is that you might have to take the square root of a negative number. That would happen actually if you were to take a look at what you have to do when you're looking at the thing. But of course, I usually mean when we're looking for velocity in that context. So, but I agree with you that it's going to be down and to the left because we're going to assume the motion is going to go, that the block is going to slide. We're assuming that 40 kilograms is enough to move this 20 kilograms and to overcome not only friction is what we're trying to find, but to overcome what the force is right here. By the way, that is something we can also find right here, the force of the spring. And then lastly here, force of the tension. One of the reasons why I would ask a question like this is to see, can you look through and actually observe what's taking place? It'd be out of your comfort zone. Feel free to eat some pizza, by the way. You don't want to have to take it home with you.
So because that it's a one-to-one rope, does the force of tension in AB also equal the force of tension in BC?
Great question, no.
Okay.
Why do you think? Anybody?
Pulley, is it massless?
Yes, the pulley is not massless. So the pulley is going to take some force to accelerate it. It doesn't want to accelerate because it has mass. So this segment will have a different tension than that segment right there, which was going to lead us in a second to our next thing that we have to do. So we have, this is going to be the mass of A times the acceleration of A. What do we need to do next, do you think? Well, let's actually set this up, as Annabelle said. Some of the forces in the y prime direction, mass times acceleration in the y prime direction, but we know that's going to be 0 because it isn't flying off of this surface at any time soon. So we could look at that and say we have Fn is positive, And we have a negative mg, but cosine of theta. Nobody else in the y prime direction. So Fn is equal to mg cosine theta. So friction force is mu mg cosine theta. Or maybe I should have written friction force is mu Fn, and that's there. Skipped a step. We can also set up an equation, but we're going to be left with unknowns that we can't fix, so we're going to have to find something else to do. So let's go FT, because that's our main guy. That's the main thing we want to find out. We're going to have minus F, what did I write, SPR for the spring. We're going to have minus our friction force. We can substitute that. And then minus mg sine theta. I think I got everybody, right? So I got 4 things. Right. And then ma acceleration of A. Can we find this?
Yes.
Yeah, that's just going to be, oh, right over here, FSPR. I'm going to make sure my camera can catch me. Actually, I think it was pointing up really high. I need to probably look and see what this looks like. Oh, I get it there. Yeah, right there. I think I got it. It's going to be an awesome video. I just know it. So that's going to be K times del. And our K, let's get some numbers in here, 2,000. And our del is 0.02. And a smarter man could do that in his head. 0.02. 40. So 40 newtons. We could also, while we're here, get this one, right? So he is going to be 0.02, 0.2, sorry, 0.2. Mass 20, 9.81, cosine 20. So I think I'm right at 37.87 newtons. So Ft minus 40 minus 36.87 and then minus 20. 9.81 sine 20 equals, I'll go ahead and write 20, an acceleration of A. That adds together 20, 9.81 times 20 sine times let's see what this kind of, I think I got that right. So add that, and we're left with 144 plus 20 AA. And we can call that equation 1. All right, so we're marching through this thing. I think we got everything we possibly can. We have 2 unknowns. Here is our goal. We have to do something about this acceleration, so we need to start looking at maybe the next thing. So I want another FBD. Look on the other side of the string, because I don't think I could write on both sides of this. Well, maybe here you go. Have I told you the story of this? I always think of this. It was my first year at Coast Guard Academy, and I had an office mate. So we had a large office. We shared it together. He's a nice man. He was a very nice man. He had like a lot of little habits that drove me nuts. He used to take a pen and go click, 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 all the time. It was on the other side of the cube, right? That drove me nuts. And he had this little vocal tick as he would talk. I think it was every 2 words, maybe sometimes every 3 words. He was like, he'd be saying ah, that he had this vocal tick that he had to say all the time. I'm not even doing it justice. It's more of like there's like a foghorn. Like I even sat through one of his classes. And I was like and I would tell my wife, and my wife hears me and thinks I exaggerate sometimes because I do. And I actually recorded him one day and played it back, and she was like dying. I really thought you were exaggerating, but if anything, I was exaggerating. But anyway, he had a classroom right after me. He was in the class right after I was using a classroom. He was a very short man. Just to be mean, I'd always put this thing out there. Couldn't reach it. Yeah, I'm a terrible person. I'm admitting it. It's on camera too. All right. So anyway, let's move on to this. Where we have this little thing right there. Let's take a look at this. Right, FBD. So here is the rigid body part of this problem, and we need to accelerate this wheel, and therefore there needs to be a force difference, a force imbalance in order to accelerate something. Right? Think about sum of the forces equals mass times acceleration. They better not equal 0, because then it won't accelerate, right? There has to be a force imbalance, so therein lies the answer to that question. Will those tensions be the same? No, because it has to accelerate. And it has mass, so it's going to resist the acceleration. Therefore, the forces have to be different in order to accelerate. It doesn't have any choice. So we're going to have a tension that's going this direction that we'll call FTAB. And we'll have one coming this direction, which is FT BC. Which one's going to be larger?
FTBC,
FTBC, why?
because there's more mass on mass C than there is on mass A.
Kind of hard to say that for sure, because there's something with the angles. How about the fact that we are presuming it's going to accelerate clockwise, right? Therefore, that has to be larger than that in order to, right? It's good. It's good. I appreciate answers, by the way. It's the correction of anything that you get wrong that really leads to learning, right? You have that thing in your mind, you think one thing, and then you find out the other, and then you get an explanation, and then you absorb it and you go, oh, I got that. And then you don't make those mistakes again. So we want to embrace the mistakes. Like, they're good. That's a positive spin, but it's a true spin. So we have I of this thing, call it B, and alpha. I almost drew, I was used to momentum, almost drew an omega, because we've been doing momentum, right? But this is second law. To be complete, we should also put in reactions. And so we have, we're using MBG, and then we can call this, I like to use R's for reactions. And so here's RBX. I think we have everything we need here. Okay. So we've been using a lot of blue here. Saving this purple. Only have so much purple left. Can't find. I got to buy some purple markers. So much better. It's gonna be sad when it's gone. We're doing it about V. It does not equal 0. You just said that. Okay. Counterclockwise is positive, so we can write F. Whoop. By the way, I just noticed this should have always been FTAB. I forgot. Tab. Anyone ever drinking a tab? Do you even know the tab is a soft drink?
I got it off of Amazon.
You bought tab?
I bought a 12-pack of tab. When
Interesting.
it was available on Amazon.
Wasn't there like something in Napoleon Dynamite where they had like a tab? Something in the movie. Anyway, neither here nor there. Not, but I got this better. Okay, so I fixed that. Ooh, purple. Oh, don't die. There, I turned it a little, just twisted it a little bit, made it a little better. Okay, tab. But remember, this has got to be a moment, so we're going to have the radius RB. And it's going counterclockwise, so we're good. All right, so there's a moment. And then we also going to have TF, TBC, and then still RB. And, okay. And then, but we're going in the negative direction here. And we're going to IB, alpha. You can even go alpha B if you want. We can put a hat on top. So we don't know that, we don't know that, we don't know that. Well, great. That really helped us. See how we, yeah, you can see, oh, we can see it all the way down. Not very well, but you can see it. So let's put some values in here. F, TAB, radius is 0.25. Minus F, TBC, 0.25. Uh-oh. Starting to get into light purple. Minus, and this should be, they didn't give us a radius of gyration, so, and it must, maybe they said, maybe they, I wrote it, maybe I said it was a disk. Let's assume it's a disk.
It said it was a disc.
Yay, they did. It was me. I'm just joking. 16. Yes, they did. I'm going to like to refer to myself in the third person. Is that 2.5? 0.25? Sure. So 1/2 m r squared, and then unknown alpha b. So that wasn't a lot of fun. But we could simplify this by going this. I'll go ahead and put it over here. F TBC plus, no, minus, still says minus. Minus, and then I'll just have to do 60 times 0.25, 60 times 0.25, divided by 2, right? Because I could just divide out by 0.25 all the way along, right there. I think that's true. And I think I have 7.5 times alpha b. Here's equation 2. That's French. I've almost exhausted all of my French now. On our first cruise to Bermuda, my wife and I sat next to a couple from Canada, and the husband of the couple only spoke French. So I had to try out all the French that I knew on him.
But it's not like real French, that's like Quebec French.
Like Quebec French. But I used my Monty Python French accent,
No.
if you're familiar.
Oh,
It
no.
worked. Not on purpose. Go ahead. I blow my nose at you. Also called the King. You know the English kniggets. He was pronouncing knights. That was the word right there, by the way. FBD. Where we go? Fromage. It's me cheese, by the way. I actually surprisingly knew way more French. I don't remember what it was, but Lori was impressed by how much. Lori's easily impressed, though. Go ahead, Bob. I didn't hear that one. All right, so here we're doing an FBD and an IBD of our last thing, E, and we're hoping, praying, that this is going to give us to the promised land. So we're going to have mass of C, what do we call it? C, reflections in my way. Acceleration of C, and we're going to have the force T, BC, and we're going to have MCG. So the sum of the forces in the y direction equals mass times acceleration in the y direction up. So we have F, T, BC minus MCG equals minus MC AC. So I keep wanting to write T. What is wrong with me? I don't know. That's a lot. That's a big question. TBC equals, brought him back over to the other side. What is he? Hopefully he's enough, 40 kilograms. Because this is the thing that's driving the whole guy, right? Minus 40 AC. So just a little short calculation to get this into another equation. And then some reflection on what we needed. Times, so we had, this should be a big enough number to make this thing move. If it's not, that means the spring takes over, all right? So this is equation 3. So let's see, unknowns. We have finally found a use for the screen because you can't really read writing. See here, 1, 2, 3. We already have that guy right here. 4, 5. Yeah, 5. 3 equations and 5 unknowns. But what do we do now? How do we proceed?
Wouldn't alpha B be equal to AC divided by RB?
Yep. So we have kinematics to the rescue. You got to remember, you know, there's some simple kinematics, but a couple of other things, right? So we know that acceleration of C equals the acceleration of A, right? We could call that dependent motion if we wanted to. It's a simple one, but it's a dependent motion. So that's you can think of that as another equation, right? So even though we had this as an unknown, we also had that as unknown. So that really, this is another equation. It eliminates an unknown. And then, as Annabelle said, we also have that either one of these things is going to be equal to alpha B times RB. So you can see that's a fifth equation into there. So we could substitute into these, and I guess I'll do it right here in the middle because I spread it out all the way over there. I also set it up so that I could equate these two things. So I can make that, and then I could actually even substitute into here, right? So what I'll do, see, this requires an extra step, but mathematically, it's actually will be easier. Algebraically, it'll be easier to approach it this way, to set them up to be equal to something. The thing I want to find, but then I'll be able to find the acceleration and plug it back into here. So my goal right now is to try to find acceleration A. That's just by the way, that's just my approach to doing these problems, right? I find it's just an itty bit easier instead of mathematically to organize things, to try to like make the actual thing, which is the thing we want to find. That's the connection between these pieces. So mathematically, it's the connection. That's at least the way I think of it. So I'm going to write out 144.0 plus 20 times acceleration of A is equal to, all right, so here's an FTBC, but I already have this guy, so I'm going to write him next. And this actually, by the way, if you can understand this tip that I'm trying to give you right here, this can actually make your exams go faster. You can make your solving, I think, personally, it can make, getting through that math part of the equation, which is obnoxious, a little quicker. All right, so now I'm about to write the acceleration of C, but I've already written it out here. So the acceleration of A is what I decided was what I wanted to get. Right, so I've replaced this FTBC with this equation, so now I can continue with a minus 7.5, and now I want my alpha BC, but let's write this up here. Alpha B, excuse me, is going to be equal to acceleration of A over RB. So that guy's getting in my way. All right, acceleration of A over 0.25. So you can see here I can solve for an acceleration of A. Did I lose anyone in terms of my algebra strategy? Want me to repeat what my strategy was? There's no shame in not getting what I just said. It's higher level solution strategies, right? Not higher level. It's not higher level. It's just I struggled with algebra as a kid. You know, I missed 3 years worth of school because I went to a really bad middle school, and then when I got into high school, I really was way behind everybody else in math, and like forever after have always struggled with algebra. Just even in the relearning it for PhD classes and stuff. I was like, oh boy, man, I was resentful again. But this is my way of coping with it. It's my coping mechanism right here, is to organize. You take a look at this equation right there. I purposely, when went through there, I'm like, I foresaw that this is the thing that I want, so maybe I want to make one equation where I can focus on it. And then when I was working over here, I was like, this is one of my unknowns. I can write my equation in terms of that, and then take that one and make it equal to that one, right? And then I also saw, well, this is also an unknown. So when I come back over here, I can write it in terms of here. So now my solution is to take this one, plug it into that one, and take that one and add them together. And then replace everywhere that I see an acceleration with this kinematics, so I can isolate that one thing. And practicing that will make it easy to do on an exam. And you'll fly right through that step and get on to the next problem, and you won't run out of time. So 144 minus 392.4. It's got me nervous, because if this were any larger, this would become a negative thing. Acceleration should be a negative. Don't you agree? Well, actually, it depends on what the accelerations are. We'll see. We'll see in a second. Maybe. Nervous. I'm nervous. It actually, my acceleration might be negative. Let's check it out. No, I think, we're going to be okay. It is negative, but I see what's going to happen, right? So I'll do my in-between step. I'm going to say a negative 248.4 right here. Flip onto the other side. I'm going to take, this is going to be a negative 20 and right here, so we'll have a negative 60 right there. And then I'm going to subtract out 7.5.25 divided, so it ends up being 30 right here, so I get a negative 90. Whew. All right, I was nervous there for a second. So acceleration of A is in fact going to be positive, and therefore, all right, so I get a 2.76 meters per second squared. Can I do a quick little reflection of what happened here? If there were no spring, no friction, and no mass at A or B, what would the acceleration of C be?
mg.
Yeah, 9.81, right? So it's less than something than 9.81, right? It's not accelerating because we have all these things that are holding it back. Like the mass of A is holding it back, but also because of the, a portion of it is going down that way right there. But we also have the friction going on here, we have the spring going on here. All of those things are making this less than 9.81. So 9.81 is the ceiling, and if we got something higher than 9.81, we did something wrong. But we can now plug it back into 1 and go FTAB. Go 144 plus 20 times 2.76, and we can get the answer. $7,949 newtons is the answer. I don't know 100% that I didn't screw something up along the way, but you can kind of see the solution mindset, the approach onto the thing. This is too long. It's too long of a problem to do as part of an exam. But it's did I do something wrong?
No, I was just wondering, is that 144 or 1,440?
It should be 144, I think. And where did he come from? He came from a collection of things, right? 40, yeah, okay, so it was 40 plus 36.87 plus 67.10, so 144 is presumably what those add up to, if I did it correctly.
I got 199.2.
Right here?
For the force of tension in AB.
For this one?
Yeah.
Okay. So I probably just hit my computer, my calculator wrong. Would doubt it. So yeah, that makes actually a lot more sense. So I don't know what I was talking and you're writing at the same time. Yeah, 199.2. You would think that would be when they were interviewing you to be a professor, they say, can you talk and write at the same time? Can you think and talk and write? No, can't. Something's got to give. All right, so we had a request for Newton's second law. That's a Newton's second law. It's a tough one. I think I'm trying to remember. I had a student who had to do make up for a incomplete, and I think that was an exam problem I gave.
How about rigid body acceleration?
Okay.
With the three-body diagram.
Well, are you saying a 3-body or a 3-body?
What's the difference between those?
Mm.
Well, let's do something that will come in the test.
Oh,
What about?
you came back to me. I knew you would. I have an exam from the, I actually have two. The Coast Guard Academy, we go over the problem that's in there. They have a, so we should probably have done. See if I can find it. Thank you, sir. Good to see you. David.
Mas.
So nice to meet him twice. I bet he hasn't heard that before.
Pepperoni, I don't like pepperoni.
So let me think if I can find this thing. I guess I'll use the document camera. Ooh.
You don't eat the crust?
Huh?
You don't eat the crust?
It's too spongy.
It's protein.
Protein? Is there protein?
No.
These are carbohydrates.
Fiber.
Well, if you think about pepperoni as a little protein.
There you go.
Some egg on the ground.
And nitrates. Nitrates.
Now I feel more like a.
So let us try Alright, so we go camera. Oh.
It's all for me.
You know where? There you go. That's up. And of course you can't see it.
Pepperoni though. All this stuff. 1.5 pepperoni.
Alright, so I gotta clean this up a little bit. Thank you. See you soon. We have a problem right there. Okay, so this was an Coast Guard Academy final exam problem. Thank you. Have a great weekend. Oh, I got so much to do this weekend. Oh. So at the instant given, member AB has an angular velocity of 3 radians per second counterclockwise. and an angular acceleration of 2 radians per second squared counterclockwise. Determine the velocity at slider block B at this instant. So they cheated and tried to fool you into thinking it was an acceleration problem when they were just asking for velocity. What an evil thing to do. They fooled me because I falsely remembered that this was an acceleration problem. But let's do this anyway as an acceleration problem and pretend what they really wanted was to find the acceleration of C. So,
Is there any way you could bump up the brightness on that?
oof, is there a way? I don't think I have those capabilities. I'm going to rewrite the thing onto the on here anyway. So
Okay.
hopefully that'll help. I don't know if these people can see that. All right. So let's check out what our angles are. Look at this stupid 3, 4, 5 thing. I hate that. I know the semester must be near an end because, whoop, there you go. Because all my markers are gone. Like shake it like a Polaroid. That's actually, that song's been gone for a long time. 7 inches.
I do everything in pens.
And they give me this right here. It's like weird. 5 inches. It's probably some shortcut we can make because of the way they put this thing together. 5 inches. And they said that this thing is on a 5. Is it 3, 4? Yeah, 3, 4. And anybody else? Okay, so this has this and this. So this is 2 radians per second squared. And this is 3 radians per second. Anybody else? I think we have all the information we need. So we can proceed.
What is the what's the mass of the block of the nut?
Oh, well, we're not going to do, this is only kinematics. We just dropped the, well, we're going to need to do there's going to be one on the exam, so I thought that would be worthy of trying to do an example here. So as a refresher too, where do you think the ICR is going to be located here?
Yeah, on the bottom. Like
Bottom, I think the
right
bottom,
below the
right?
right.
Like let's draw something perpendicular to this line right there, right? Right there. Can you see why? And draw the velocity of this thing. Is going that right there, right? I didn't letter these things, so it was A, B, C, all right? So A, B, that's velocity B, C. So here's a line that, remember when it's one of these, you can always draw a line through the link, extend the link. And then if you have like a slope right here, it's going to be perpendicular to the slope. So I kind of made it curve run down here, but so that's the ICR right in there. This always bothers me right here, the 3, 4, 5. I don't think in those terms, I think in terms of angles. But I can look at this and say, well, the velocity must be in that direction because we must be taking an omega BC, must be right there from our ICR. Does anyone feel uncomfortable with that in terms of the ICR thing?
The 345 or the,
No, just the location of the ICR.
no, no.
All right, so try to draw this out here separately. First off, let me see if I can figure out what this angle of this leg is going to be. Oh, this is also one of those cutesy triangles, right? This is a 5, and so this is a 12, so this must be 13. 5, 12, 13 triangle. I always hated those. That's actually real, right? Am I misremembering as a one of those standard triangles? I could be wrong, by the way. I'm wrong a lot.
12, 5, 13, yeah.
Yeah. So I need that. I need some angles. It looks. Oh, I made it look like 45. This is like really bad habit. It's a bad trap to fall into when trying to figure something out. Because it's great. It's nice to have as close as you can to the right angles onto the thing. So an angle on here is going to have the 12, it's going to be the tangent or inverse tangent of 12 over 5 and 810. So that's going to be 67.38 degrees. Right in there. And this thing right here, let's see if we can, this angle of a slope, this angle should be, that's the 36 degree right there, right? That's where you take 3 divided by 4, it's 0.75 obviously, and take the inverse tangent, and you can get 36.87 degrees. I prefer doing that. So when it comes to this right here, that's going to be the same angle right here. Remember, that's not the same as that. So we're kind of talking like that right there is the correct angle. And then perpendicular to that, purple, I must use some orange. We don't use orange enough. That's going to be that guy, which is going to form, let's see, here's going to be, that angle is also going to be 36.87. So that's going to be the inverse, or not the inverse, but the supplement, that's the right word, supplement, 53.13 degrees. And so the ICR into that. Here's my way of looking at this. This is also going to be, that's going to be 36, right? 0.87. And then this right here is going to be yes. Also be the 22.62 degrees. So this is going to be RB with respect to ICR. This is RC, ICR, RC with respect to ICR. So, law of sines. We have a bunch of angles and only one side that we know, and we happen to know it because of the 5, 7. So we have the 12, 5. So this is 13 inches right there. So we say 13 divided by sine of 36.87 is going to be equal the only one we really need if we're doing an acceleration problem is this one, RB with respect to ICR, divided by the sine, and I'll put them in here, 67.38 plus 53.13. That's a lot. 67.38, 53.13, add them together, take the sine, multiply that by 13, divide that by the sine of 36.87. I bet this is going to come up with some like whole number. It's going to like piss me off. No, it's not. So it'll be 18.67 inches. We could also, if we wanted to, so that we could find the velocity of C, might as well take the RC with respect to ICR, and then what's that, the sine of 22.62. So RC with respect to ICR. So 22.62 sine multiplied by 13 divided by 36.87. It's 8.333 inches. So something I could have found before, still can. Worth doing is do the analysis of the first link. Find VB, which is going to be omega AB times LAB, which is going to be 3 times 7. 21. I could do that. So we could find omega BC, it's going to be VB right here, so we have this VB. There's our omega BC divided by R B with respect to ICR. So 21 divided by 18.67. .125 inches per second, or radians per second. And then the velocity of C is going to be omega BC times RC with respect to ICR, 1.125, and 8.333. Boom. 9.375 inches per second. So if that was the problem being asked on that exam, that would be the entirety of it. But here if we were doing acceleration, something I hadn't put, I could have done it before. We could put this acceleration and that acceleration. And so this is the acceleration of B in the y direction, which is actually the acceleration of B with respect to A, yes, normal, so that's omega AB squared times LAB. I don't know if I captured all this on camera. Keep forgetting there's a camera there. Should be 3 squared times, where'd you go, 7. 9 times 7 is S23? He did actually just ask me that. That's what you could say. You know, I'm not sure if he's qualified to be my professor. He can't do,
So calculated for?
that's right. Or your abacus or your slide rule. No, that's not true. We already established I don't know how to use slide rule. I could use an abacus, but I think it's just for adding. I bet there. You know, here's one. Here's a side note. Here's like a completely unnecessary thing to include. I had this like vague memory of this advertisement. There's like this craze that was hitting America called Chisenbop. It came from Asia. I think it was Japan. It was Korea. And little kids could do all kinds of math faster than people could solve it with the calculator by going like this right here. This right here. You would learn, and you'd be able to keep track of stuff. They could do division, multiplication. I think they could even do square roots. Just by going like da, 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 and they get the answer. And they have them on news programs all the time. And I swear. And I looked it up. It was true. Still a thing. You can learn it yourself. Look it up. It had the craziest name though. It was like, it sounds like Bop by Hanson, which you wouldn't remember. I don't know why you wouldn't even know that song exists. But it was like, that was also Bop, ba, ba, bop. That's a stupid song. Let's go back to Harrison. So you had 2 times 7. Ooh, 14. Gotcha. Inches per second squared. All right, so now we go to the difficult one to do. This is the 3 diagram method, and I think that's what Alejandro was referring to, as opposed to the, you said 3 body diagram, so there's a 3 body diagram, and then there's 3 diagram method, and we had them interspersed, right? That's okay. Maybe I'm going to change the thing. That sounded better. I like what you said better than mine. Want to try to avoid the 45-degree angle trap. So Jess, flip it. There you go. Okay. Red is a good color for accelerations. All right, so here at the top, we know these 2 values. We know that value, and we know this value. We have actual values for it. We call it ABX, maybe ABY. And we know this direction. And having seen these already, we have a strong suspicion. So we can make a guess. It's a hazardous guess, but we can make a guess that the acceleration of C is going down that way. We could pick the other direction if you wanted to, but I have a strong feeling that this is going to be the way to go. And in terms of angles, that right there is the angle we want, right? It's the same as that angle. The same as that 36.87. We agree? Well, that's hard to see. I don't know if that camera's getting any of this. I feel bad, but keep going. So that's the 36.87 degrees in there. So we put on both of these places to represent the translation. And I didn't write a plus. I want to put a plus on it. And because we use this as the reference, that becomes the pinned one in the 3rd diagram. And here becomes some ugliness, right? Here's the tedious part of this, but it's a little practice, get faster at it. You're going to have an acceleration coming that way. Always do, if it's got an angular velocity. Always coming up towards the center here. And then we have to choose a direction for this next one. Let's choose that direction. So what we've done is we made a guess, alpha BC, go in that direction, which is a guess. So I'll label these best I can. acceleration of C with respect to B, normal. Acceleration of C with respect to B, tangential. And here's the hard part, is the angles. So the angle we figured out for this one is 67.38. So that right there is 67.38. Between the horizontal and this. So that would mean that right there is also 67.38, right? All right, so we're set up for success now. The rest is just keeping track of what's going on in the diagram and writing out the equations correctly. Unfortunately, yeah, I think we're gonna have 2 equations and 2 unknowns. There's no shortcut in this. Kind of a pain in the ass. I usually try to have a problem on an exam where you can take a shortcut, but here we are in our 2 equations and 2 unknowns hellscape. No, that's not true. Okay, so over here, let's write out our main equation. Acceleration of C is equal to the acceleration of B plus the acceleration of C with respect to B, tangential, plus the acceleration of C with respect to B, normal. And this one right here, we can find this guy. He's going to be omega BC squared LBC. So that's going to be the 1.125. And this right here, this is the reason we had to do that whole thing. Should be all over there. And then the length of this is 13. So as a value 1.125, we square it, multiply by 13, and you get 16.45 inches per second squared. I guess I could do it underneath it. I don't want to, I guess I can. So I'm going to have a negative AC in the x direction times the cosine of 36.87 equal to negative ABX 14 plus alpha BC times 13 times the sine of 67.38. Gotta read it smaller. Just cram it in there. Plus, all right, so that was the tangential, plus 16.45 times the cosine of 67.38. And I don't think it makes sense to write the next one underneath here. So, but I will, let me fix this thing up. Maybe what I'll do is I'll solve for AC. Right, so I'll say, I got my 16.45 times the 67.38 cosine times, okay, that's positive, and then, but I need a 14 subtracted from it. All right, so I have a negative value for that. I could divide that by the cosine of 36.87, which is 0.8, makes sense, right? So, so I have, and I'm gonna, with the negative right there, I end up with a 9.590. It was negative, but then this negative returned to there, all right? And then I'm also dividing my 13 times 67.38 sine times, ends up being 12, right? That makes sense, duh. Divide that by 36.87, cosine of 36.87, which is 0.8. Boom, I get 15. And it's going to be negative. So I'm going to get a negative 15 times alpha BC. There's all kinds of room to screw that up. In the y direction, I'm going to have a negative AC times the sine of 36.87. Equal to ABY, which is at 63, but it's negative. And so we still have this guy right here, which is, you know, of course, remember that was alpha BC times L BC. So also negative. Yes, negative. And alpha BC times 13 times the cosine right there, right? Because we're looking, it's this guy right here, and it's going downwards. That's why it's negative. And we take the cosine of 67.38. And then lastly, it is going in the positive direction. This one. 16.45, and it's going to be the sine of 67.38.
Professor?
Yep.
Is that 63 being multiplied by the alpha, or?
It's supposed to be a negative right there.
So subtract?
Yeah. Because this right here is the acceleration of c with respect to b in the tangential, but we're only taking, and right here it's going in the vertical direction. So it's right there. It's that guy, that's component of that vertical component. Boy, okay, so we have a lot of things to keep track of. 16.45 times the sine of 67.38, which I'm sure is going to be something. No, it's not. Okay, shut up. Okay, good. And take 63, subtract from it, and then divide by 36.87, or the sine of 36.87. So this is, and the sign flips, so 79.69. Okay. And then, so this could be a positive right here. We take 13, multiply them by cosine of 67.38. That's 5. Divided by 36.87 sine divided. I think you're right, 8.333 alpha BC, and then set these two things equal to each other. So 9.590 minus 15 alpha BC is equal to 79.69 plus 8.333 alpha BC. Alpha BC. I think it's going to be negative. I think we had the wrong direction. I think so. Yeah, because we're going to pull this over to that side, makes it negative. So 9.59, add that. And then we're going to divide, and we're going to add 15 and 8.333. Add them, divide them. You get negative 3.004. Suspicious of dropping a sig fig along the way. And then you can plug it into either one. So you go 9.590 minus 15 times negative 3.004. And we end up with a positive number. So we actually picked the correct direction of C, but we picked the wrong direction of the alpha. It can be quite confusing sometimes to try to rationalize what's going on, but it's also so easy to make mistakes with the signs and math and that kind of thing along the way. This is a really challenging problem. It's too challenging to really ask for an exam. It took us 35 minutes. That's a long time that's professor time, right? I usually try to multiply it by 2 or yeah, this is the way you think of it in terms of like, okay, this is what you could expect a student to try to do. Sometimes 2.5. Get that wrong a lot. It's hard to, difficult to judge. But it's also, trying to encourage you to try to find those places where you can speed things up. Have a great weekend.
What about the FE exam?
Say again?
The FE exam?
Yep.
What kind of questions would you kind of expect on the FE exam?
Usually, I say if you take the number of exams and the number of questions and the total time given, I think it comes out to about 2 minutes, somewhere like that, like 1.9 minute per question. So when teaching or when giving a FE prep class, I usually tell people to divide questions into 3, and it's all about the individual, about I could do this in 30-second questions, right, or less. I could do this in 3 minutes or less. I have no chance of answering this question in under 3 minutes, right? I was like, okay, what you want to do is go through and answer all those under 30-second questions as fast as you can. And never psych yourself out if you find that there's you have to keep that positive attitude on the thing. And then go back through and after you've done that, go back through and do all the 2-minute questions, or I usually don't actually say 3-minute questions. Usually, I think 2 minute. I have all this written down. And then the others, if you make sure you have spare time to go through and then wheedle down, like, okay, is this even in my? Have I any clue on how to do that? And the rest just put in numbers, right? Don't wait to the end to just put in guesses.
Generally, how many questions?
It's written down in the on our exam or on the FE exam.
FE, no, not ours.
Okay, the FE exam, I think it's like I want to say it's like 110. Some stupid thing like that right there. If you want to know more things about the FE, there's a lot of information on the NCEES, I think it's NCEES is the National Council of Engineering Examiners and Surveyors. I don't know why the surveyors always get lumped together with the engineers, but they do. I'm not saying surveying isn't important. It just doesn't seem important to me. Sorry, surveyors. That seemed mean. But if you go go back to FE exam, exams, FE exam, I just wrote that thing, licensure. There's a thing in here about, I'll give you, oh, here you go. It's a 5-hour and 20-minute exam. And 110 questions. So 5 hours and 20 minutes turns out to be, can't do math, 5 times 60, boom, and 20. So 320 minutes, but you have 110 questions. So that comes out to 2.9. All right, so memory didn't work well. 2.9 minutes per question. And they give you sample exams in here, but there's also, I would really highly advise that you buy some preparatory materials and do some review, maybe even enroll in some type of online class. There's a ton of stuff. We've been talking about forever, well, I've been talking about since I got here, because I noticed there was only a civil engineering FE prep class, not a mechanical one, that we needed a mechanical one, because it's a really good thing for your program to encourage your students to get their to take the FE. It's really smart to take it when you're a senior in college and not wait, not procrastinate, because it's over a wide range of stuff, and in your career you will narrow down very quickly to a range of things that you learn a lot about and are comfortable with, but then have purged those little memory things and stuff like fluid mechanics and thermo, if you're like a structures guy, and vice versa if you're a fluids guy. So I just, it isn't a mandatory thing for a mechanical to have a PE license, but it sure does look good. Did you notice how that's how, I mean, did you go to the thing on Wednesday? Yeah, I didn't take, well, somebody actually gave me, I took a scan of the list. I don't know what I said I was going to do with that, but I'll try to, you'll have to remind me what I said I was going to do with that.
Brownie points. Brownie
Brownie points, because there were brownies there, so you got those brownie points already. I'm joking around, but I don't know, I'll think about something. But anyway, you notice how Dr. Slaybach introduced him about he's a professional engineer, he's a PE. It is a point of pride to say that I'm a PE. You stick it on your business card. People looking at it, literally, I hand a business card and goes, oh, you're a PE. It is a thing to take pride in. When you're applying for a job, I'm a PE. I'm going to start a company, right? I have a PE. You know, or boy, it'd be great to have another PE on our staff, right? Someone that can stamp stuff. It's a responsibility too, but it's a good thing to have. So the FE is the first step and opens up doors to, and it looks good, but by the way, your employer will go, and it used to be, I don't know about this, it used to be a really long time after you took the exam before you found out whether you passed or not. And so I think they threw me a party. Yeah, at my first job. Because I'd already been employed and working there, and I found out that I passed. So like 6 months had passed, right? And they're like, hey, all right, take it, it's kind of a thing, and we used to call engineering training by the FE, used to be called the engineering training, the EIT. I think they just liked the way the FE matched with the PE thing, But they might even call it, your certificate might, for many states, might still call you an engineer in training, the EIT. But it's like a rite of passage, just like passing the bar exam for a lawyer. It's like, it's part, and it's, it is identical to that, because that's a license that allows you to practice engineering. You can still be an engineer and not without that license, but you can't advertise yourself as an engineer and without a license. I pay to renew my PE every year to the Connecticut Department of Consumer Protection. That's the mindset of why the thing exists. So anyway, this is an exam review session. So what kind of problem would you like to go through? Or are you just so burnt out you just don't want to do it anymore? Because I almost kind of wanted to try to influence you. Okay. I'm so burnt out. I want to go play with my 3D printer. Actually, I have to go grade some more. But let's do some more problems, because I'm excited about doing dynamics. You could give us that. I know. But you might be nervous. I want to ease your nerves. Don't be nervous. Just do well. That's all. Easy.
So on Tuesday's class, are we just gonna be reviewing like all of dynamics, like what are we?
I was thinking of taking requests, but also just trying to do sort of a reflection back to, and a lot of times I'll go over the parts of the FE as a coincidence. There's an equation book that you could download off that website that would be available to you during taking the FE. And I find in a lot of classes, it's a good, I don't know if it's a good way, it's the way I do it. I can't tell you measurably whether it's effective or whether students give a shit. But for me, I can try to convince you, this is why I taught this in this class, right? This is like, in the context of an FE equation booklet, this is what the people, the wise people that wrote the thing, they decided, this is what a minimally qualified engineer coming out of college should know. Right? So at least that's the message I take from it. So I kind of put it into context. I'm like, okay, here's here, and here's there, and you can see it's all the same stuff. Right? And that we've been thorough, that we covered, so that you can see like, okay, is this education that you're getting sufficient? Right? That's a question you should be asking all the time. I know I did because I went to a weird school. It was literally to learn to drive ships. Like, okay, but am I an engineer? Like, or am I a choo-choo train type of engineer, right? They call that guy an engineer too. Right? The garbage man, he's also a sanitation engineer, right? It's like, yeah, it's you put engineers, but am I an engineer, right? The kind that can solve problems, right? Yeah. So taking the FE for me, or the EIT for me, was like, how did this go? Right? Did they set me up for success, this school? Was it worth it? Was it a quality education? So I showed, I would say when you're taking the FE, that's a thing to like, just want to measure. How do I stand against my, other people in the same situation? Most everybody just coming out of college in their senior year. So when I use that as a means of review because it seems like it's pertinent and something to do. I'm not sure if it's the right thing. So I'll also try to encourage you to fill out the course evaluation if you haven't already. So might give you some time. I've yet to do that. I keep forgetting to. So I keep meaning to, and then I dismiss people. I go, shit, I meant to do this, and then don't do it. It's really important to me that I get as many people as possible, so I can get a self-reflection for me. Like, okay, what did I do differently? What can I do differently? And then also, I had thought about. I haven't done this before, but if you haven't noticed, I assigned the concept inventory thing again. I actually have done that before with my mechanisms class, and they're seniors, right? As a way of trying to do a refresh on dynamics, because it was a couple years since they took it, and I make, okay, take this as part of your participation, take it again, and see, and then I go through it afterwards. So I thought about going through it afterwards, right? Just to go, and then you could go, oh, I see, and those are the best, right? Where you can get, and so maybe that's what I'll do in the last class. Try not to take quite as long as I have. Sometimes I made the entire class going over the thing. But you can kind of see, by the way, it's a lot of it's reading the question right away. So it's tough.
For homework 24, it said it was due 3 days ago.
Oh, are you serious?
Yeah.
I was so tired last night. I was so beat. I'll fix it. I apologize. I'll fix it. I was so, it was probably because okay, you don't even care about it, but on the interface, you have to click next month and then click onto the thing right there. So because we're right there near the end of the month, it was like, I had to pick the May 3rd or something like that, whatever, May 2nd onto the thing. So I was going through there because I had to do it 6 times. No, actually I guess I had to do it 8 times. Actually, I had to do it 16 times. I had to click on that thing 16 times, so I'm not surprised I made one mistake. I probably made 4 mistakes. That's probably how tired I was. But yeah. Thank you for letting me know. I'll fix it. I'll have to look. I should have re-looked it over, but re-looked it over. It's like 11:30 at night. I'm still here. Yeah. Kicking myself. knowing I had to get up early again.
How was the expo?
I think it was better than most years.
I liked it this year.
Yeah. I got to tell you, I didn't go to. Oh, I think I'm going to stop this. We're done.
Yeah, we're done. Yeah, we're done.
Thank you. So brain.